Black holes, the dark architects of the universe. Stop, just for a moment. Think about the most powerful thing you have ever seen. A hurricane, a volcanic eruption, a nuclear explosion. Now multiply that power by 1 billion, by 1 trillion, by a number so large that your mind cannot even grasp it. Now imagine that power trapped in a single point, a point so small that it has no size at all, a point where gravity becomes infinite, where time stops, where space itself collapses into nothing. This is not imagination. This is real. This exists in our universe right now. It is called a black hole, and it is the most terrifying, most mysterious, and most powerful object in all of existence. You have heard of black holes. You have seen them in movies. You have read about them in books. But I promise you this: what you are about to hear will change the way you see the universe forever. Because black holes are not just cosmic monsters. They are the architects of galaxies, the engines of creation, the gateways to the unknown. And perhaps, just perhaps, they are the key to understanding everything. So hold on, because we are about to fall into the abyss. Part 1. The darkness beckons. Chapter 1. The cosmic abyss. Imagine a place in the universe where gravity is so intense that not even light can escape. A place where the very fabric of space and time is torn apart, where the laws of physics as we know them cease to exist. This is not science fiction. This is the black hole. The most mysterious, most powerful. Every black hole begins with a death, the death of a massive star. When a star at least 20 times heavier than our sun runs out of fuel, its core collapses under its own immense gravity. The outer layers explode outward in a supernova, but the core keeps falling inward, compressing into an infinitely dense point, a singularity. The singularity is where our mathematics breaks down. Density becomes infinite. Space and time lose all meaning. It is not a place in space, it is the end of space itself. To understand the density of a black hole, consider this. If you compress the entire planet Earth into the size of a marble, it would become a black hole. And that is just the beginning. Some black holes contain the mass of billions of suns, compressed into a region no larger than our solar system. Chapter 2. The anatomy of darkness. A black hole is not simply a hole in space. It has structure, layers of impossibility that challenge everything we understand about reality. The outermost boundary is called the ergosphere. Here, space and time are dragged along with the black hole's rotation at nearly the speed of light. Nothing can stand still within this region. Everything must spin with the black hole's immense rotational energy. Beneath that lies the photon sphere. This is a region where light itself is trapped in orbit. Photons circle the black hole like race cars on a track, creating a brilliant ring of fire visible to us from Earth. And finally, we arrive at the event horizon, the point of no return, the boundary beyond which escape is impossible. If you cross this line, you would never be able to send a signal back to the outside universe. To an outside observer, you would appear to slow down, freeze in time, and slowly fade away, never quite crossing the horizon, but never truly existing anymore. The event horizon is not a physical surface. It is a mathematical boundary, but it is the most absolute boundary in the universe. Once matter crosses it, all information about that matter, its composition, its history, its identity, is lost to the universe. As you fall toward a black hole, the gravitational pull on your feet is exponentially stronger than on your head. You are stretched, elongated, and eventually torn apart into a stream of subatomic particles. This phenomenon is called spaghettification. Part 2. Seeing the Invisible. Chapter 3. The Image That Changed Everything. Black holes are invisible. They emit no light. By definition, they absorb it all. So how do you photograph something that refuses to be seen? The answer lies in the brightest light around the darkest darkness. As matter falls toward a black hole, it accelerates to incredible speeds, heating up to billions of degrees. This superheated gas emits X-rays and radio waves, creating a glowing halo around the black hole. A silhouette against a brilliant sunrise. We weren't photographing the black hole itself. We were photographing its shadow. The event horizon casts a shadow against the glowing accretion disk. That shadow is what we captured. April 10th, 2019. For the first time in human history, we saw the face of a black hole. This was M87 star, a supermassive black hole 55 million light-years from Earth, with a mass 6.5 billion times that of our Sun. What made this image possible was not a single telescope, but a network of 8 radio observatories spread across 4 continents, synchronized with atomic clocks accurate to a nanosecond. Together, they created a virtual telescope the size of Earth itself. The data they collected was too massive to transmit over the internet. It had to be shipped on hard drives, physically flown across the world to processing centers. The reconstruction of this image took 2 years. The algorithms used were developed by a graduate student who wrote code that could fill in the gaps in the data, transforming scattered radio waves into a coherent picture of cosmic darkness. The image confirmed Einstein's theory of general relativity once again. The size and shape of the shadow perfectly matched what relativity predicted. Einstein was right yet again. Chapter 4. The Two Faces of Black Holes. Black holes come in 2 primary varieties, and they could not be more different. Stellar mass black holes are born from the death of individual massive stars. They range from about 3 to 100 solar masses. They are scattered across our galaxy. There may be 100 million of them in the Milky Way alone. The closest one to Earth is just 1,560 light-years away. It is invisible to our eyes, but its gravitational pull on a nearby star betrays its presence. But stellar mass black holes are dwarfs compared to the titans that reside at the centers of galaxies. Supermassive black holes contain millions to billions of solar masses. Every large galaxy seems to have one at its heart. Our own Milky Way hosts Sagittarius A star, a black hole 4 million times the mass of our Sun. The one in the galaxy M87 is 1,600 times larger. How do these giants form? That remains one of astrophysics' greatest mysteries. Some believe they grew from smaller black holes that merged over billions of years. Others propose they formed directly from the collapse of immense gas clouds in the early universe. Perhaps they were born from the death of the very first stars, which were hundreds of times heavier than anything that exists today. When supermassive black holes feed, they become quasars, the brightest objects in the universe. A single quasar can outshine an entire galaxy of 100 billion stars. The energy is generated as matter spirals toward the black hole, converting gravitational potential energy into radiation with terrifying efficiency. Part 3. The Dance of Giants. Chapter 5. The Music of Spacetime. Black holes do not live in isolation. When 2 black holes orbit each other, they create ripples in the fabric of spacetime itself. Gravitational waves. These waves carry the energy of their motion, causing the black holes to slowly spiral inward. For millions of years, they dance. They circle each other faster and faster, releasing gravitational energy, losing orbital momentum. And then they collide. 2 black holes become one. The energy released in this collision is greater than the combined energy of every star in the observable universe, and we can detect it. September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first direct gravitational wave signal. It came from the merger of two black holes, 36 and 29 solar masses, colliding 1.3 billion light-years away. When I first saw that signal, I knew what it was immediately. It was exactly what we had predicted. Einstein had predicted these waves 100 years ago, and here they were, arriving at Earth exactly when we were ready to listen. Since that first detection, we have observed dozens of black hole mergers. Each one tells us more about how these giants form, evolve, and interact. We have seen mergers of unequal masses, mergers with rapid spin, and mergers so distant that they happened when the universe was only a third of its current age. Chapter 6: The Mystery of the Missing Rings. In 2023, NASA's Chandra X-ray Observatory discovered something unusual. A supermassive black hole in a distant galaxy had rings. 3 concentric rings of X-ray light surrounding it. These are not physical rings. They are light echoes. When the black hole emits a burst of X-rays, those rays travel outward, bounce off dust clouds, and some of that reflected light reaches us at different times, creating the illusion of rings. Each ring represents a different dust cloud at a different distance. By studying these rings, astronomers can map the distribution of gas and dust around distant black holes, understanding how they feed and grow. Even more remarkably, astronomers have found a galaxy with 2 supermassive black holes at its center, orbiting each other. They are currently 3,000 light-years apart, too far to merge anytime soon. But in about 100 million years, they will spiral into each other and merge, releasing gravitational waves that will echo across the universe. We have found that most galaxies have a central black hole. When galaxies merge, their black holes merge. This is a fundamental process of cosmic evolution. The black holes at the centers of galaxies are intimately tied to the galaxies themselves. They grow together, they influence each other, they shape the fate of entire galaxies. Part 4: The Paradoxes. Chapter 7: Hawking's Radiation and the Information Paradox. For decades, black holes were thought of as eternal prisons. Nothing could escape, not even light. But in 1974, a young physicist named Stephen Hawking made a discovery that shattered this picture. Near the event horizon, quantum mechanics dictates that particle-antiparticle pairs are constantly popping into existence. Normally, they annihilate each other instantly. But at the edge of a black hole, one particle can fall in while the other escapes. The escaping particle carries away energy, making the black hole lose mass. This is Hawking radiation. Given enough time, every black hole in the universe will evaporate. A stellar mass black hole would take about 10 to the power of 67 years, far longer than the current age of the universe. The supermassive ones would take up to 10 to the power of 100 years. But this created a profound paradox. In quantum mechanics, information about a particle, its spin, its momentum, its identity, can never be destroyed. If a black hole evaporates, what happens to all the information that fell into it? Does it disappear? If so, quantum mechanics must be wrong. This was not a small problem. The information paradox was the most pressing question in theoretical physics for decades. It forced us to reconsider our most fundamental assumptions about reality. Hawking spent his final years trying to solve this puzzle. In 2016, he and his collaborators proposed that the information might be encoded in soft hair, low-energy particles and gravitational waves that exist at the event horizon, carrying imprints of everything that fell in. If true, the information is not destroyed. It is simply transformed, and stored at the event horizon. When the black hole evaporates, that information is released back into the universe. Stephen always believed that information must be preserved. He used to say, "Quantum mechanics is not wrong. Gravity is not wrong. It is our understanding that is incomplete." I think we are finally starting to see how it all fits together. Chapter 8. The Firewall Controversy. If Hawking's paradox seemed daunting, things got even stranger in 2012 when a group of physicists proposed something radical. They argued that to resolve the information paradox, the event horizon must not be a smooth, gentle boundary. Instead, it must be a firewall, a violent, high-energy barrier that incinerates anything trying to enter. An astronaut crossing the horizon would not simply pass through, they would be vaporized instantly. This contradicted Einstein's equivalence principle, which says that falling into a black hole should feel like free fall, with no local effects. If firewalls exist, gravity is not locally equivalent to acceleration. Something fundamental about physics would have to break. Firewalls were a shock. They created a dilemma. Either we lose quantum mechanics, or we lose gravity, or we accept that black holes have firewalls. None of the options are comfortable. The debate continues to this day. Some physicists propose that black holes are actually wormholes, bridges to other universes. Others suggest that they are fuzzballs, string-theoretic objects without a distinct event horizon. What I love about black holes is that they challenge our deepest assumptions. They force us to think harder, to question our theories, to dream of new physics. That is where progress comes from. Part 5. The Future. Chapter 9. Black holes as energy sources. As daunting as black holes are, they may also be the most powerful energy sources in the universe. How do you extract energy from a black hole? Roger Penrose, in 1969, proposed that energy could be extracted from a rotating black hole. His idea, now known as the Penrose process, involves throwing matter into the ergosphere, the region just outside the event horizon where space is dragged along. If a particle enters the ergosphere and splits into two, one piece falls into the black hole, but the other can emerge with greater energy, stolen from the black hole's rotation. This is not perpetual motion. It is extracting rotational energy from the black hole, slowing its spin in the process. A more efficient method is the Blandford-Znaiec process, where magnetic fields near the black hole extract energy, powering the incredible jets seen emerging from quasars. If we could harness this, a single supermassive black hole could power a civilization for billions of years. The energy stored in a rotating black hole is staggeringly large. If we could tap into it, we could power interstellar travel. We could build Dyson spheres around black holes instead of stars. It is the stuff of advanced civilizations. Could future humans do this? It would require technology far beyond what we possess today. But the physics is sound. A supermassive black hole could serve as a cosmic battery, offering an inexhaustible source of energy for a spacefaring civilization. Chapter 10. The Ultimate Fate of the Universe. What happens to black holes in the very far future? The universe is expanding, and galaxies are drifting apart. Eventually, the last stars will die. The last galaxies will dissolve. The universe will grow dark and cold. But black holes persist. They will outlast all matter, all energy, all structure in the universe. Stellar mass black holes will evaporate after 10 to the power of 67 years. Supermassive black holes will take 10 to the power of 100 years. After that, the universe will be nothing but radiation. Photons, neutrinos, and gravitational waves, drifting forever in an endless, featureless void. The universe will have reached its maximum entropy. This is the heat death of the universe. Black holes represent the ultimate end state of the universe. They are the future toward which everything is heading. It is a haunting thought that our universe, so rich and complex, will one day be nothing but black holes and empty space. But this is billions upon billions of years away. For now, we have the privilege of existing in a vibrant, alive universe, looking out at these cosmic giants and wondering. Chapter 11. A window into other universes. There is another, more speculative possibility, that black holes are not endpoints, but doorways. The mathematics of general relativity allows for white holes, the opposite of black holes, where matter and energy can only emerge. Some physicists suggest that black holes and white holes could be connected, forming wormholes, bridges between distant regions of spacetime, or even between different universes. We know that the singularity at the center of a black hole is an indication that our physics breaks down. It is not that the singularity is real, it is that we do not yet understand the physics that governs that realm. When we do, we may discover that black holes connect to something beyond, perhaps to other universes, or to new dimensions. To truly understand black holes, we need a theory of quantum gravity, a framework that unites general relativity with quantum mechanics. Physicists are working on this problem through string theory, loop quantum gravity, and other approaches. When we solve it, we will not only understand black holes, we will understand the fundamental nature of reality itself. Part 6. Conclusion. Chapter 12. The Final Frontier. We have come a long way, from Einstein's thought experiments to the first image of a black hole, from Hawking's theoretical radiation to the detection of gravitational waves, from the information paradox to the firewalls and fuzzballs. We have made remarkable progress in understanding these cosmic giants. But we have barely scratched the surface. The singularity remains a mystery. The information paradox still lacks a complete resolution. The relationship between quantum mechanics and gravity is still unclear. The Event Horizon telescope is already looking toward its next target. Sagittarius A star, our own galactic black hole. Future telescopes, some in space, some on the ground, will capture even sharper images, revealing the dynamics of the accretion disk, the jet formation, and perhaps even the elusive photon ring. The laser interferometer space antenna will detect gravitational waves from supermassive black hole mergers across the universe. The James Webb Space Telescope will peer deeper into the early universe, revealing how the first black holes formed. But perhaps the greatest discoveries lie not in the technology, but in the questions themselves. What happens at the singularity? Is there a way to escape a black hole? Do they connect to other universes? Are we, in some sense, living inside a black hole right now? Black holes are not just objects in space. They are windows into the deepest mysteries of existence. They challenge us to think beyond the obvious, to question our assumptions, and to dream of what lies beyond the horizon. In the end, black holes remind us of the most important truth. We are part of something vast, mysterious, and utterly beautiful. We are made of stardust, shaped by gravity, illuminated by the light of distant suns. And we are driven by an almost primal need to understand our place in the cosmos. The horizon is not the end. It is a beginning of a journey into the unknown, a journey that is as much about ourselves as it is about the universe. What lies beyond? Perhaps we will never know. But that is what makes the journey worthwhile. Journey to the edge of infinity. Now imagine that power trapped in a single point, a point so small that it has no size at all, a point where gravity becomes infinite, where time stops, where space itself collapses into nothing. This is not imagination. This is real. This exists in our universe right now. It is called a black hole, and it is the most terrifying, most mysterious, and most powerful object in all of existence. Birth of the beast, when stars die. Every black hole begins with a death, the death of a star. But not just any star, a star so massive that its own weight becomes its destroyer. For billions of years, a star burns bright. Nuclear fusion in its core converts hydrogen into helium, releasing energy that pushes outward against gravity. This balance keeps the star alive. But when the fuel runs out, gravity wins. The core collapses. In less than a second, a star larger than our Sun crushes itself into a ball only a few kilometers across. The outer layers explode outward in a supernova, scattering elements across the cosmos. But the core keeps falling. It falls forever. It becomes a black hole. A black hole is not empty. It is the most dense thing in the universe. Imagine the entire Earth compressed into the size of a marble. That is the density of a black hole. Now imagine something 1,000,000 times heavier. That is how extreme these objects really are. The invisible monster. Black holes are invisible. They emit no light. They reflect no light. They absorb everything that comes near them, including light itself. That is why they are called black. But how do we know they exist if we cannot see them? We see their effects. When a black hole is near a star, it pulls gas from the star. This gas spirals inward, forming a glowing disk called an accretion disk. This disk gets so hot that it emits X-rays and radiation. We can see those X-rays. We can map the orbits of stars around an invisible object. We can measure the mass of that invisible object. And when we do, we find something so heavy that it can only be one thing: a black hole. The first black hole ever discovered was Cygnus X1, found in 1964. It is about 15 times the mass of our Sun. Since then, we have found hundreds. But we believe there are millions more, perhaps even 100 million in our galaxy alone. 3 kinds of darkness. Not all black holes are the same. They come in 3 main sizes, each more extreme than the last. The smallest are called primordial black holes. They are purely theoretical. They may have formed in the first moments after the Big Bang, when the universe was dense and chaotic. Some could be as small as an atom, but as heavy as a mountain. They have never been confirmed, but some scientists believe they could be everywhere, passing through Earth without us even noticing. Next are stellar mass black holes. These are born from dying stars. They are between 3 and 100 times the mass of our Sun. They are scattered across the galaxy, hidden in darkness. And finally, the giants, the supermassive black holes. These are millions to billions of times heavier than our Sun. They sit at the center of almost every large galaxy. Our Milky Way has one. It is called Sagittarius A star. It is 4 million times the mass of our Sun. It sits 26,000 light-years away, in the direction of the constellation Sagittarius. The physics of madness. The event horizon. Point of no return. The defining feature of a black hole is the event horizon. This is the boundary around the black hole. Once something crosses this boundary, it can never return. Not even light can escape. That is why it is black. The event horizon is not a physical surface. It is a mathematical boundary, a place where gravity becomes so strong that escape velocity exceeds the speed of light. If you were standing at the event horizon and looking outward, the entire universe would appear to be frozen in time. Everything outside would look slow, stretched, and dim. But you would not be standing there for long. You would be falling inward, pulled by a force that is impossible to resist. The event horizon is often called the point of no return, because it truly is. Once you cross it, you are no longer part of our universe. Your fate is sealed. you will fall toward the center, and what happens there, we do not fully understand. The singularity, where physics breaks. At the center of every black hole is the singularity. This is where all the mass of the black hole is concentrated into a single point, a point with zero volume and infinite density. This is where our physics breaks down. The laws of gravity, the laws of quantum mechanics, the laws of space and time. None of them work at the singularity. It is a place where the universe stops making sense. Time stops at the singularity. Space stops existing. The rules that govern the rest of the universe do not apply here. Some scientists believe that the singularity is not real. They believe it is a sign that our understanding of physics is incomplete, that a new theory is needed, a theory of quantum gravity. Until we have that theory, the singularity remains a mystery. It is the ultimate unknown, a place we can never visit, a place we can never observe, but a place that exists right now in the heart of every black hole. Spinning and charged black holes. Not all black holes are the same. Some spin, some carry an electric charge, and these properties change how the black hole behaves. A rotating black hole is called a Kerr black hole, after the physicist Roy Kerr, who first solved Einstein's equations for a spinning black hole. These black holes drag space and time with them as they spin. This effect is called frame dragging. It creates a region around the black hole called the ergosphere, where space itself moves faster than the speed of light. If you entered the ergosphere, you could potentially extract energy from the black hole. This is called the Penrose process. It is a way to steal rotational energy from a spinning black hole. Theoretically, you could power a civilization using this energy. Charged black holes, called Risen and Nordstrom black holes, are also possible. They have an electric charge. This creates a complex structure with multiple event horizons. But most black holes in the real universe are probably neutral and rotating. They are spinning giants, dragging space and time in their cosmic dance. The cosmic dance. Black holes and galaxies. Black holes are not isolated objects. They are connected to the galaxies they live in. There is a relationship between the mass of a black hole and the mass of its galaxy. Bigger galaxies have bigger black holes. This suggests that black holes and galaxies grow together. They shape each other. The black hole at the center of a galaxy influences how the galaxy forms stars, how it evolves, and how it dies. The black hole can heat up gas, preventing it from cooling down and forming stars. It can blast out jets of energy that push gas out of the galaxy. These jets are powered by the black hole's accretion disk. As gas spirals toward the black hole, magnetic fields channel some of that energy into narrow beams. These beams travel at nearly the speed of light, extending thousands of light years into space. Black holes are not just destructive, they may also be creative. The jets and radiation from black holes can trigger the formation of new stars in neighboring regions. Black holes are architects of galaxies. They build and destroy. They give life and take it away. The dance of two giants. When galaxies collide, their black holes collide too. Two supermassive black holes spiral toward each other in a cosmic dance that lasts millions of years. As they orbit, they emit gravitational waves, ripples in space and time. These waves carry energy away from the black holes, causing them to spiral inward. Eventually, they merge into a single, even larger black hole. This is one of the most violent events in the universe. The energy released in the merger is greater than the combined energy of all the stars in the observable universe. But we do not see it. We detect it through gravitational waves. In 2015, LIGO detected the first gravitational wave from a black hole merger. It was the collision of two stellar mass black holes, 1.3 billion light-years away. Since then, we have detected dozens more, but we have not yet detected the merger of supermassive black holes. That will require a future observatory in space, the Laser Interferometer Space Antenna, or LISA. LISA will listen to the low-frequency hum of supermassive black hole mergers across the universe. Black holes and time. Time dilation near the abyss. Einstein taught us that time is not fixed. It can slow down. It can speed up. It depends on gravity. Near a black hole, gravity is so strong that time slows to a crawl. If you watched a clock fall toward a black hole, you would see it slow down. Tick, tick, tick. Slower and slower. It would never quite reach the event horizon. It would appear to freeze in time, getting redder and dimmer until it faded away. But for the clock itself, time would pass normally. It would fall past the event horizon in a fraction of a second. This is time dilation. It is one of the most profound consequences of Einstein's theory. If you fell toward a black hole, billions of years could pass on Earth in the blink of an eye. You could travel to the future, but you would never return. The black hole would swallow you, and the universe would move on without you. Some scientists have wondered if black holes could be used as time machines. Falling into one would stretch time, but it would also destroy you. So perhaps not the best way to travel. Hawking radiation, the slow death. Black holes are not eternal. They evaporate. This was Stephen Hawking's greatest discovery. In 1974, Hawking showed that black holes emit radiation. This is called Hawking radiation. It comes from quantum effects near the event horizon. Particle-antiparticle pairs are created out of nothing. One falls in, the other escapes. This escaping particle carries away energy, and slowly the black hole shrinks. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate. A supermassive black hole would take 10 to the power of 100 years. This is longer than the current age of the universe. But given enough time, every black hole will vanish. The final moments of a black hole are violent. As it shrinks, it radiates more and more energy. In its final second, it releases the energy of millions of nuclear bombs in a burst of radiation. Then it is gone. Nothing remains. But this raises a question. What happens to all the information that fell into the black hole? Quantum mechanics says information cannot be destroyed. But Hawking radiation carries no information. So where does it go? This is the information paradox, and it remains unsolved. The mysteries remain. The information paradox explained. The information paradox is one of the biggest unsolved problems in physics. It goes to the heart of our understanding of reality. Quantum mechanics says that the universe is deterministic. If you know the state of every particle at one moment, you can predict the future and reconstruct the past. Information is never lost. It is preserved. But black holes seem to destroy information. When matter falls into a black hole, it disappears from the observable universe. When the black hole evaporates, it releases thermal radiation. That radiation contains no information about what fell in. The information is lost. This is a contradiction. Either quantum mechanics is wrong, or our understanding of black holes is wrong. Many physicists have tried to solve this paradox. Some have proposed that information is encoded in the radiation, but in a way we cannot yet detect. Others have suggested that black holes are not true black holes. They are fuzzballs or firewalls. Some have even proposed that information escapes through wormholes to other universes. The solution remains unclear. But the information paradox is a sign that we need new physics, a theory that unites gravity and quantum mechanics. wormholes and other universes. There is a possibility that black holes are not the end. They may be the beginning, a doorway to something else. Einstein's equations allow for solutions called wormholes. These are tunnels through space-time, connecting two distant regions. Some physicists believe that a black hole could be connected to a white hole on the other side. A white hole is the opposite of a black hole. Nothing can enter it. Everything can escape. If this is true, then black holes could be bridges to other universes. Falling into a black hole might not destroy you. It might transport you to another part of the cosmos or another dimension entirely. This is highly speculative. There is no evidence for wormholes, but the mathematics allows it. And sometimes, mathematics points the way to reality. Until we have a theory of quantum gravity, we cannot know for sure. But the possibility is exciting. Black holes may not just be the end of everything. They may be the beginning of something new. Conclusion. Looking into the abyss, we have come far in our understanding of black holes. From Einstein's equations to the first image, from Hawking's radiation to gravitational waves, from stellar mass giants to supermassive monsters at the heart of galaxies. But we are still beginners. The singularity remains a mystery. The information paradox remains unsolved. The connection between quantum mechanics and gravity remains unclear. Future telescopes will give us sharper images of black holes. Future observatories will detect their gravitational waves. Future theories may finally unite gravity with quantum mechanics. But perhaps the most important discovery is the questions themselves. What is inside a black hole? What happens at the singularity? Do they lead to other universes? Are we, in some sense, living inside a black hole right now? These questions are not just for scientists. They are for all of us. They remind us that the universe is vast, mysterious, and full of wonder. They remind us that we are part of something bigger than ourselves. Black holes are not just cosmic monsters. They are cosmic teachers. They challenge us, they humble us, and they inspire us to look up at the night sky and wonder. The edge of a black hole is the edge of our knowledge. Beyond it lies the unknown, and that is exactly where discovery begins. Horizon. We have stared into the abyss. We have learned how black holes are born, how they grow, how they warp space and time. We have seen their shadows. We have heard their gravitational songs. But we have only scratched the surface. The deeper we go, the stranger things become. The laws of physics bend. Reality itself begins to blur. In the first part of our journey, we explored the known. The birth of black holes, the event horizon, the singularity, the cosmic dance of galaxies and giants. But now we step beyond the horizon, beyond the known, beyond what we understand. Because black holes are not just mysteries, they are messengers. They carry secrets about the birth of the universe, about the nature of time, about the very fabric of reality. This is not the end of the story. This is where the real story begins. The echoes of creation. The universe began with a bang. A single point of infinite density expanded outward, creating space, time, and all matter. That point was a singularity. Black holes also contain singularities, points of infinite density where physics breaks down. This is not a coincidence. Some physicists believe that black holes and the Big Bang are connected, that inside every black hole, a new universe is born. This idea is called black hole cosmology. It suggests that our universe may have been born from the collapse of a black hole in another universe. Our Big Bang was the birth of a black hole in a parent universe. If this is true, then black holes are not endings, they are beginnings. They are cosmic wombs. Every black hole in our universe could be the seed of a new universe. And inside those new universes, new civilizations may be asking the same questions we are asking. We cannot test this idea, not yet, but it is a beautiful possibility. That black holes are not just destroyers, they are creators. Primordial black holes, ghosts of the past. There is another class of black holes that may exist. They are called primordial black holes. They are not born from stars. They are born from the chaos of the early universe. In the first fraction of a second after the Big Bang, the universe was incredibly dense. Regions of extreme density could have collapsed directly into black holes. These primordial black holes could be any size, some as small as an atom, some as heavy as a planet. If they exist, they would be invisible. They would not have accretion disks. They would not emit X-rays. They would drift through the universe, silent and undetected. But we may be able to find them. They could pass through stars, causing tiny vibrations. They could pass through planets, leaving microscopic tunnels. They could even be responsible for dark matter, the invisible substance that holds galaxies together. Some scientists believe that primordial black holes are everywhere. They may be passing through Earth right now. We just cannot see them. They are the ghosts of the ancient universe. The quantum abyss. Black holes and quantum mechanics. Einstein's theory of general relativity describes gravity. It tells us how black holes warp space and time. It is a masterpiece of physics, but it is incomplete. Quantum mechanics describes the smallest things: atoms, particles, forces. It is also a masterpiece, but it does not include gravity. When we try to combine them, they break. They give us infinite answers. Nonsense. This is the greatest problem in physics, the problem of quantum gravity. Black holes are where this problem becomes real. At the event horizon, quantum affects matter. At the singularity, gravity is infinite. Both theories are needed, but neither works. To understand black holes fully, we need a theory of quantum gravity. String theory is one candidate. Loop quantum gravity is another. Both are beautiful. Both are unproven. Until we have a theory of quantum gravity, black holes will remain the most mysterious objects in the universe. Black hole entropy, the information hidden inside. In 1973, Jacob Bekenstein proposed that black holes have entropy. Entropy is a measure of disorder or hidden information. Bekenstein argued that a black hole's entropy is proportional to its surface area, not its volume. This was a radical idea. It suggested that black holes are not simple. They contain information, and that information is stored on their surface, like a hologram. This led to the holographic principle, the idea that all the information in a volume of space can be stored on its boundary. Our universe may be a hologram, a three-dimensional reality projected from a two-dimensional surface. If this is true, then black holes are not holes. They are information storage devices. They encode everything that falls into them on their event horizons, and when they evaporate, that information may be released back into the universe. This is still a theory, but it is gaining support. The holographic principle may be the key to understanding quantum gravity, and black holes are the laboratory where we test it. Time and destiny. Black holes and the arrow of time. Time flows in one direction. We remember the past. We cannot predict the future. This is the arrow of time. It is one of the greatest mysteries in physics. Black holes may help us understand it. Near a black hole, time slows down. Time becomes distorted. It becomes almost meaningless. Inside a black hole, time and space swap roles. Normally, we can move freely in space, but not in time. Inside a black hole, we would be able to move freely in time, but not in space. Time becomes a dimension we can navigate. This is mind-bending. It suggests that inside a black hole, the arrow of time breaks down. Past and future lose their meaning. Everything that ever fell into the black hole may still be falling. From its perspective, time has stopped. Some physicists believe that time does not exist at the fundamental level. It is an illusion. Black holes may be the places where that illusion is revealed. The end of time, black hole evaporation. Time will eventually end, not because the universe stops, but because everything decays. Black holes are the ultimate timekeepers. They outlast everything. Stars die, galaxies dissolve, protons decay, but black holes persist. A stellar mass black hole takes 10 to the power of 67 years to evaporate. A supermassive black hole takes 10 to the power of 100 years. To put that in perspective, the current age of the universe is 10 to the power of 10 years. When the last black hole evaporates, the universe will be empty. No stars, no planets, no life. Only radiation drifting in the endless void. Time will have no meaning. There will be no events to mark its passing. This is the heat death of the universe. It is the ultimate fate of all things. But it is so far in the future that our minds cannot truly grasp it. For now, we live in a universe full of stars and galaxies and black holes. We live in the middle of time. The human perspective. What would it be like to fall in? Imagine you are falling into a black hole. You are in a spacesuit. You are falling feet first. What do you experience? At first, nothing unusual. You are in free fall. You feel weightless. The stars around you begin to stretch. They become brighter. They turn red. Then they fade. As you approach the event horizon, you see the universe behind you speed up. Billions of years pass in seconds. You watch galaxies form and die. You watch the universe age and fade. Then you cross the event horizon. You do not feel anything special, but you are now trapped. No signal you send can ever reach the outside universe. You continue falling toward the singularity. The gravity on your feet becomes stronger than on your head. You are stretched. Your body becomes a thin stream of atoms. You are spaghettified. And then, at the singularity, physics breaks down. No one knows what happens. You may be crushed into nothing. You may enter another universe. You may simply cease to exist. Falling into a black hole is the ultimate journey. It is a journey beyond space and time, beyond reality itself. Black holes in human culture. Black holes have captured the human imagination. They appear in movies, books, and art. They are symbols of the unknown, the terrifying, the sublime. In the movie Interstellar, a black hole is a gateway to another dimension. In science fiction, black holes are weapons, time machines, and doorways to other worlds. They represent the limits of human understanding. They are the darkness we cannot see into. But black holes are not just metaphors, they are real. They exist in our universe, and they remind us that we are small, that our understanding is limited, that there is always more to discover. The mystery of black holes calls to something deep within us. It is the same drive that made our ancestors look up at the stars, the same drive that led to the first telescopes, the same drive that gave us science. We are explorers. We are curious. We are not content to stay in the light. We must look into the darkness. The future of black hole research. The next generation of telescopes. We have taken the first image of a black hole, but it is blurry. It is low resolution. It is just the beginning. The Event Horizon telescope is improving. New observatories are being added. New algorithms are being developed. The next images will be sharper. They will show details we have never seen. We will see the photon ring, the bright ring of light around the black hole. We will see the shadow in higher resolution. We will see the dynamics of the accretion disk, the jets, the magnetic fields. Future telescopes in space will capture even more. The Black Hole Explorer mission is being planned. It will observe black holes in X-rays and gamma rays. It will map the environment around black holes in unprecedented detail. And then there is LISA, the Space-Based Gravitational Wave Observatory. LISA will detect the mergers of supermassive black holes. It will open a new window on the universe. It will reveal the cosmic history of black holes. Could we ever visit a black hole? Visiting a black hole is impossible with our current technology. The nearest black hole is 1,500 light-years away. Even at the speed of light, it would take 1,500 years to reach it. But in the far future, perhaps humanity will travel to the stars. Perhaps we will build generation ships. Perhaps we will develop faster-than-light travel. Perhaps black holes will become destinations. If we ever visit a black hole, it would be the ultimate adventure. We could study it up close. We could test our theories. We could learn the secrets of gravity and time. But visiting a black hole is also dangerous. The gravity is immense. The radiation is lethal. The tidal forces are destructive. We would need technology far beyond anything we have today. Perhaps we will never visit a black hole in person. Perhaps we will send robotic probes. Perhaps we will observe from a safe distance. But the dream of visiting a black hole is a dream worth having. The cosmic perspective. Black holes and the meaning of existence. We began this journey with a question. What is a black hole? We have learned that they are the graves of massive stars, the engines of galaxies, the portals to unknown worlds. But perhaps the most important thing we have learned is something else, something about ourselves. Black holes remind us that the universe is vast, that it is mysterious, that it is full of things we do not understand. They humble us, they challenge us, they inspire us. We are small, we are temporary, we are fragile, but we are also curious. We are explorers, we are thinkers. We are part of the universe trying to understand itself. Black holes are not just objects in space, they are mirrors. They reflect our own quest for knowledge, our own struggle to understand the cosmos, our own journey into the unknown. We may never fully understand black holes. We may never visit them. We may never know what lies beyond the horizon. But that is okay, because the journey itself matters. The questions we ask matter. The wonder we feel matters. Black holes are the edge of our knowledge, but they are also the beginning of our imagination. The horizon is not the end. We have reached the end of our journey, but the journey is not over. The horizon is not the end. It is only the boundary of what we know. Beyond the horizon lies the unknown, the singularity, the quantum realm, the possibility of other universes, the mystery of time, the question of existence itself. These are questions we may never answer, but we will keep asking, we will keep exploring, we will keep pushing the boundaries of human knowledge. Black holes are the ultimate frontier. They are the darkness we cannot see into, but they are also the light that guides us forward. They remind us that there is always more to discover, that the universe is endless, that the adventure never ends. So look up, look at the stars, look at the darkness between them. Somewhere out there, a black hole is spinning. Somewhere out there, matter is falling. Somewhere out there, the universe is revealing its secrets. And we are watching, we are listening, we are learning. The horizon is not the end, it is a beginning.